The Tetrahedral-Octahedral Honeycomb, alternated cubic honeycomb, is a quasiregular space-filling tessellation, or honeycomb, in Euclidean 3 space. It is composed of alternating regular octahedra and tetrahedra in a ratio of 1:2. Other names include half-cubic honeycomb, half-cubic cellulation, or tetragonal disphenoidal cellulation. John Horton Conway calls this honeycomb a tetroctahedrille, and its dual a dodecahedrille. It is vertex-transitive with 8 tetrahedra and 6 octahedra around each vertex. It is edge-transitive with 2 tetrahedra and 2 octahedra alternating on each edge. A geometric honeycomb is a space filling of polyhedral or higher dimensional cells, so that there are no gaps. It is an example of the more general mathematical tiling or tessellation in any number of dimensions. Honeycombs are usually constructed in ordinary Euclidean, flat, space, like the convex uniform honeycombs. They may also be constructed in non-Euclidean spaces, such as hyperbolic uniform honeycombs. Any finite uniform polytope can be projected to its circumsphere to form a uniform honeycomb in spherical space. It is part of an infinite family of uniform honeycombs called alternated hypercubic honeycombs, formed as an alternation of a hypercubic honeycomb and being composed of demi-hypercubed and cross-polytope facets. It is also part of another infinite family of uniform honeycombs called symplectic honeycombs. In this case of 3 space, the cubic honeycomb is alternated, reducing the cubic cells to tetrahedra, and the deleted vertices create octahedral points. As such, it can be represented by an extended Schläfli symbol H4,3,4 as containing half the vertices of the 4,3,4 cubic honeycomb. There is a similar honeycomb called Gyrated Tetrahedral-Octahedral Honeycomb, which has layers rotated 60 degrees so half the edges have neighboring rather than alternating tetrahedra and octahedra. The Tetrahedral-Octahedral Honeycomb can have its symmetry doubled by placing tetrahedra on the octahedral cells, creating a non-uniform honeycomb consisting of tetrahedra and octahedra, as triangular antiprisms. Its vertex figure is an order 3 truncated triachis tetrahedron. This honeycomb is the dual of the triachis truncated tetrahedral honeycomb, with triachis truncated tetrahedral cells. For an alternated cubic honeycomb, with edges parallel to the axis and with an edge length of 1, the Cartesian coordinates of the vertices are, for all integral values, ijk with I plus j plus k even. I, j, k. There are 2 reflective constructions and many alternated cubic honeycomb ones. Examples. The alternated cubic honeycomb can be sliced into sections, where new square faces are created from inside of the octahedron. Each slice will contain up and downward facing square pyramids and tetrahedra sitting on their edges. A second slice direction needs no new faces and includes alternating tetrahedral and octahedral. This slab honeycomb is a scaliform honeycomb rather than uniform because it has non-uniform cells. The alternated cubic honeycomb can be orthogonally projected into the planar square tiling by a geometric folding operation that maps 1 pairs of mirrors into each other. The projection of the alternated cubic honeycomb creates 2 offset copies of the square tiling vertex arrangement of the plane. Its vertex arrangement represents an A3 lattice or D3 lattice. This lattice is known as the face-centered cubic lattice in crystallography and is also referred to as the cubic close-packed lattice, as its vertices are the centers of a close packing with equal spheres that achieves the highest possible average density. The Tetrahedral-Octahedral honeycomb is the 3-dimensional case of a symplectic honeycomb. Its Voronoi cell is a rhombic dodecahedron, the dual of the cuboctahedron vertex figure for the tetroct honeycomb. The D+3 packing can be constructed by the union of 2 D3, or A3, lattices. The D plus N packing is only a lattice for even dimensions. The kissing number is 22 as equal to 4, 2n1 for n8, 240 for n equals 8, and 2n, n1, for n8. Union set symbol the A3 or D3 lattice, also called A43 or D43, can be constructed by the union of all 4 A3 lattices, and is identical to the vertex arrangement of the disphenoid tetrahedral honeycomb, dual honeycomb of the uniform bitruncated cubic honeycomb. It is also the body-centered cubic, the union of 2 cubic honeycombs in dual positions. Union set symbol equals dual of equals union set symbol. The kissing number of the D*3 lattices A and its Voronoi tessellation is a bitruncated cubic honeycomb, containing all truncated octahedral Voronoi cells. The 4,3,4 Coxeter group generates 15 permutations of uniform honeycombs, 9 with distinct geometry including the alternated cubic honeycomb. The expanded cubic honeycomb, also known as the runcinated tesseract honeycomb, is geometrically identical to the cubic honeycomb. The 431,1 Coxeter group generates 9 permutations of uniform honeycombs, 4 with distinct geometry including the alternated cubic honeycomb. This honeycomb is one of 5 distinct uniform honeycombs constructed by the K3 \_8_3 Coxeter group. The symmetry can be multiplied by the symmetry of rings in the Coxeter-Dinkin diagrams. The cantic cubic honeycomb, cantic cubic cellulation or truncated half-cubic honeycomb is a uniform space-filling tessellation, or honeycomb, in Euclidean 3 space. It is composed of truncated octahedra, cube octahedra, and truncated tetrahedra in a ratio of 1:1:2. Its vertex figure is a rectangular pyramid. John Horton Conway calls this honeycomb a truncated tetroctahedrille, and its dual half-oblate octahedrille. There are 2 reflective constructions and many alternated cubic honeycomb ones. Examples: the Runsick cubic honeycomb or Runsick cubic cellulation is a uniform space-filling tessellation, or honeycomb, in Euclidean 3 space. It is composed of rhombic octahedra, cubes, and tetrahedra in a ratio of 1:1:2. Its vertex figure is a triangular frustum, with a tetrahedron on one end, cube on the opposite end, and 3 rhombic octahedra around the trapezoidal sides. John Horton Conway calls this honeycomb a 3-RCO-trille, and its dual quarter cubill. The dual of a Runsick cubic honeycomb is called a quarter cubill, with Coxeter diagram, with faces in 2 of 4 higher planes of the B4 \__B_4 431,1 symmetry fundamental domain. Cells can be seen as 1/4 of dissected cube, using 4 vertices and the center. 4 cells exist around 6 edges, and 3 cells around 3 edges. The Runsick cubic honeycomb or Runsick cubic cellulation is a uniform space-filling tessellation, or honeycomb, in Euclidean 3 space. It is composed of truncated cube octahedra, truncated cubes and truncated tetrahedra in a ratio of 1:1:2, with a mirrored sphenoid vertex figure. It is related to the Runsick cantillated cubic honeycomb. John Horton Conway calls this honeycomb a FDCO-trille, and its dual half-pyramidal. The dual to the Runsick truncated cubic honeycomb is called a half-pyramidal, with Coxeter diagram. Faces exist in 3 of 4 hyperplanes of the 431,1 B3 \__B_3 Coxeter group. Cells are irregular pyramids and can be seen as 1/12 of a cube, or 1/24 of a rhombic dodecahedron, each defined with 3 corners in the cube center. A related uniform skew-pyrohedron exists with the same vertex arrangement, but triangles and square removed. It can be seen as truncated tetrahedra and truncated cubes augmented together. The gyrated Tetrahedral-Octahedral Honeycomb or gyrated alternated cubic honeycomb is a space-filling tessellation, or honeycomb, in Euclidean 3 space made up of octahedra and tetrahedra in a ratio of 1:2. It is vertex uniform with 8 tetrahedra and 6 octahedra around each vertex. It is not edge uniform. All edges have 2 tetrahedra and 2 octahedra, but some are alternating, and some are paired. It can be seen as reflective layers of this layer honeycomb. This is a less symmetric version of another honeycomb, Tetrahedral-Octahedral Honeycomb, in which each edge is surrounded by alternating tetrahedra and octahedra. Both can be considered as consisting of layers 1 cell thick, within which the 2 kinds of cells strictly alternate. Because the faces on the plane separating these layers form a regular pattern of triangles, adjacent layers can be placed so that each octahedron in one layer meets a tetrahedron in the next layer, or so that each cell meets a cell of its own kind. The layer boundary thus becomes a reflection plane. The latter form is called gyrated. The vertex figure is called a triangular orthobicupola, compared to the tetrahedral-octahedral honeycomb, whose vertex figure cube octahedron in a lower symmetry is called the triangular gyrobic cupola, so the euro prefix is reversed in usage. The geometry can also be constructed with an alternation operation applied to a hexagonal prismatic honeycomb. The hexagonal prism cells become octahedra, and the voids create triangular bipyramids which can be divided into pairs of tetrahedra of this honeycomb. This honeycomb with bipyramids is called the Tetrahedral-Octahedral Honeycomb. There are 3 Coxeter diagrams, which can be seen as 1, 2, or 3 colors of octahedra. The gyro-elongated alternated cubic honeycomb or elongated triangular antiprismatic cellulation is a space-filling tessellation, or honeycomb, in Euclidean 3 space. It is composed of octahedra, triangular prisms, and tetrahedra in a ratio of 1:2:2. It is vertex-transitive with 3 octahedra, 4 tetrahedra, 6 triangular prisms around each vertex. It is one of 28 convex uniform honeycombs. The elongated alternated cubic honeycomb has the same arrangement of cells at each vertex, but the overall arrangement differs. In the elongated form, each prism meets a tetrahedron at one of its triangular faces and an octahedron at the other. In the gyro-elongated form, the prism meets the same kind of deltahedron at each end. The elongated alternated cubic honeycomb or elongated triangular gyroprismatic cellulation is a space-filling tessellation, or honeycomb, in Euclidean 3 space. It is composed of octahedra, triangular prisms, and tetrahedra in a ratio of 1:2:2. It is vertex-transitive with 3 octahedra, 4 tetrahedra, 6 triangular prisms around each vertex. Each prism meets an octahedron at one end and a tetrahedron at the other. It is one of 28 convex uniform honeycombs. It has a gyrated form called the gyro-elongated alternated cubic honeycomb with the same arrangement of cells at each vertex.